This module introduces data structures, algorithms, and the principles of computational complexity. Learners will become familiar with a variety of data structures and understand their similarities and differences. Both linear data structures, such as arrays and lists, and nonlinear data structures, including graphs and trees, will be introduced. Time and space complexity, including notation for and analysis of complexity, are introduced as core considerations for algorithmic design. A range of popular sort search and pathfinding algorithms are introduced. Learners will gain practical experience in writing pseudocode for algorithms and using this to write, test, and debug programmed implementations of algorithms. Data structures include linear data structures like arrays, lists, linked lists, stacks, queues, sets, dictionaries, and nonlinear data structures like graphs and trees. Considerations for choosing data structures include the impact on the time an algorithm takes to run and the space it takes up on the disk. These considerations serve as an introduction and motivation for the next learning objective. A data structure is a way of organizing and storing data to enable efficient access and modification. It acts as a framework or blueprint that instructs the computer on how to work with the data. Core components include data, links or pointers, operations, and constraints. Data structures can be categorized into linear and nonlinear types. Linear data structures store data in a linear or sequential order, while nonlinear data structures arrange data in a hierarchical or interconnected way. Linear data structures store data in a linear or sequential order, similar to a train where each item has a clear next and previous item. Nonlinear data structures, on the other hand, are arranged in a hierarchical or interconnected way. Like a family tree or city map, examples of linear data structures include arrays, linked lists, stacks, and queues. Nonlinear structures include trees, graphs, and tries. Each type has its specific use cases and benefits. Data structures are important because they enhance efficiency, scalability, and clarity in algorithms. They help manage memory effectively and allow for cleaner, more maintainable code. The right data structure can improve algorithm performance significantly, such as using a binary search on sorted arrays. They are essential for handling large datasets or real-time processing. Understanding data structures is fundamental to software and systems design. Operations on data structures include access, insertion, deletion, and search, each with different time complexities. Arrays offer constant time access but have linear time insertion and deletion. Linked lists provide constant time insertion and deletion but have linear time access. Stacks and queues offer constant time for access, insertion, and deletion. Hash tables provide constant time search, while binary search trees offer logarithmic time for access, insertion, and deletion. A hash table stores data in key-value pairs and uses a hash function to convert keys into array indices. Collisions are managed by chaining or open addressing. For example, a dictionary in Python can store names and ages. Allowing fast lookups. Hash tables are used in caching, symbol tables in compilers, and database indexing. They provide efficient data retrieval and management. Different types of data structures fit different problems and are performance-oriented. They form the foundation of computer science and are the backbone of software and systems design. Using the proper data structure can lead to faster algorithms and more efficient solutions. Data structures are essential for organizing data, managing resources, and improving code clarity. They are a critical component of any computational solution. Linear data structures store data sequentially, like a train where each item has a clear next and previous item. Linked lists are a type of linear structure where each node contains data and a pointer to the next node. They allow dynamic memory usage and come in variants like singly, doubly, and circular linked lists. Real-world analogies include treasure hunt clues, where each clue leads to the next. Use cases include dynamic memory applications and undo or redo operations. Stacks follow a last-in-first-out structure where only the top is accessible, used in function call stacks and backtracking. Queues follow a first-in-first-out structure where elements are enqueued at the rear and dequeued from the front. Used in CPU scheduling and message queues. Variants include circular queues, priority queues, and dequeues. Real-world analogies include a stack of plates or a queue in a bank. Use cases include scheduling tasks and traversing graphs. Nonlinear data structures are hierarchical, like trees, or interconnected, like graphs. Trees have nodes with parent-child relationships used in file systems and database indexing. Common tree types include binary trees, binary search trees, AVL trees, heaps, and B trees. Graphs consist of nodes and edges used in social networks and GPS navigation. Tries are used for fast prefix searches, like autocomplete. These structures handle complex relationships and are crucial for efficient data management. Trees are hierarchical structures with nodes, where each node has a parent-child relationship. The root is the top node and branches extend to leaf nodes. Types of trees include binary trees, where each node has at most 2 children, and AVL trees, which are self-balancing. Trees are used for efficient searching and sorting. Real-world examples include organizational charts and file systems. Graphs consist of nodes, called vertices, and edges connecting them. They can be directed or undirected, weighted or unweighted, cyclic or acyclic. Graphs are represented using adjacency lists or matrices. Real-world examples include social networks and maps. Use cases involve GPS navigation, internet routing, and modeling relationships in data. Graphs are versatile for representing complex data relationships. Tries, also known as prefix trees, store words or prefixes with nodes representing characters. They enable fast prefix-based lookups useful in autocomplete and spell checkers. Heaps are complete binary trees maintaining a heap property. Used in priority queues and heap sort algorithms. Real-world applications include event-driven simulation systems. Both structures optimize specific operations for efficiency. Hash tables, also known as maps or dictionaries, store data in key-value pairs using hash functions. They allow constant-time lookups, making them efficient for tasks like caching and indexing. Real-world analogies include library index card systems. Hash tables manage collisions through chaining or open addressing, ensuring data is stored and retrieved efficiently. They are a cornerstone of data management in computing. Time complexity varies across data structures for operations like access, search, insertion, and deletion. Arrays offer constant time access, while linked lists provide efficient insertion and deletion. Binary search trees offer logarithmic time for operations, while hash tables provide constant time search. Graphs require more complex traversal logic. Understanding these complexities helps in choosing the right structure for specific tasks. Different data structures offer unique strengths and weaknesses. Arrays offer fast access but slow insertion and deletion. Linked lists excel in fast insertion and deletion but have slower search times. Hash tables provide fast lookups while binary search trees maintain order with balanced performance. Tries excel in prefix searches while graphs are ideal for mapping relationships. Choosing the right structure is key to efficient algorithm design. The choice of data structure impacts the time complexity of operations, space complexity, and scalability. Fast lookups benefit from hash tables, while sorted data suits binary search on arrays. Balanced binary search trees offer good average case performance. The right structure ensures efficient data management and processing. Understanding these impacts guides better algorithmic decisions. Different data structures affect key operations like search, insertion, and deletion. Arrays require shifting elements for insertion and deletion, making them costly for large data. Linked lists and hash tables offer faster inserts. Binary search trees maintain order but require time for insertion. The choice of structure impacts performance and efficiency. Analyzing these impacts helps in selecting the optimal structure for specific needs. Real-world examples illustrate the impact of data structure choices. For spell checkers, tries provide efficient prefix searches compared to arrays. Browser history benefits from linked lists for intuitive navigation. Task schedulers use queues or priority queues for order and urgency. Social networks benefit from adjacency lists for sparse networks. These examples highlight the importance of selecting the right data structure for specific applications. Arrays offer fast access but slow modifications. Binary search trees balance order and performance. In conclusion, understanding and selecting the appropriate data structure is fundamental to effective software design and algorithm development. The right data structure leads to efficient data handling, faster processing, and optimal resource usage. It directly enhances the performance and scalability of real-world applications, contributing to a smoother and more responsive user experience. Whether you're tackling a coding challenge or architecting complex systems, data structures serve as the foundation of reliable and efficient computational solutions. Thank you for watching this video.